Okay, so the three problems that we're going to work on are 2, 10, and 13. 2 is straight up solving. You're going to use the NPR formula, which is NPR equals n factorial over n minus r factorial. So if we have np4 or npic4, we have n in for n, so we have n factorial here, over n minus r would be n minus 4 factorial, equals 40 multiplied by, I'm going to put our NPR fraction right here. This time n, first number in the expression NPR is n minus 1, so we have n minus 1 factorial. To substitute n minus 1 in for r. In the bottom, I'm going to use brackets here because there's a parentheses there. So our n is, it's n minus r, and n in this case is n minus 1. So that's our n minus r in this case is 2. All right, we want to figure out how to simplify and then solve this. So my first suggestion would be cleaning up the denominator there on the right hand side, so I'll quickly do that. In fact, we'll do it this way. That's just be n minus 1 minus 2 would just result, oh, you know what, I forgot the factorial symbol, so that should be n minus 3 when I combine the negative 1 and the negative 2, so I have n minus 3, and I forgot this before, but it should have a factorial in there. All right, so before we continue on with this problem, as this is probably the first time you've seen factorial, let's look at a concept, a side concept, before we go about how to grapple with how to solve this. If I have 5 factorial over 4 factorial, that would be 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. So we see the 4s, the 3s, the 2s cancel, so we're left with 5. So when we have a number, factorial, divided by 1 less than that number, 4 is 1 less than 5, we could write it like this, 5 minus 1, we see we end up getting the number 5. And of course, if it was flipped, it would be the same. So what this indicates is if we are dividing two factorials and the integers that are being factorialized, I suppose, are close to each other, then we can cancel things out nice and neat. And that's what we aim to do within this equation. So all that being said, we see that the n and the n minus 1 are really close to each other, and the n minus 4 and the n minus 3 are really close to each other. So I'm going to aim to get this n minus 1 factorial over here and the n minus 4 factorial over to this side. I'm just going to kind of leave that 40 there. So first thing we're going to do is move the n minus 4 factorial to the left-hand side. The way we do that is by multiplying both sides by n minus 4 factorial. These sides would cancel. What we do to one side, we do the other. So an n minus 4 factorial. Now this will give us n factorial over, or nothing actually. Just have n factorial over here. This may look a little confusing, but I want to do this one step at a time. So we have the 40, the n minus 1 factorial over n minus 3 factorial, and then we also have an n minus 4 factorial in the numerator up here. We want to now get rid of the n minus 1 factorial to the other side, so we want to divide by it, or which is the same as multiplying by the reciprocal, so we're going to do that on both sides. Note, this is just solving. I know this may be a little uncomfortable for you, given this factorial notation is something a little different than what you're used to seeing, but essentially we are just solving an equation. So now we have an n factorial over n minus 1 factorial here equals, we have a 40 in the numerator, we have an n minus 4 factorial, and all divided by an n minus 3 factorial. So now we're going to use that same principle that we had with 5 factorial divided by 4 factorial, but now it's n and n minus 1. So if I look at the left-hand side, what does that mean? And note, you don't have to write this. I'm trying to help you understand what n factorial means when you're looking at it with variables. What we do is we take n, multiply it by decreasing integers down to 1. Well, the integer just less than n would be n minus 1, just like 5, one integer less than it is 4, and we get 4 by taking 5 minus 1. So we can write the integer previous to an integer. If an integer is n, the integer previous to it is n minus 1. And the one previous to that would be n minus 2. Just like if we have 5 times 4 times 3, 3 could be represented as 5 minus 2. Now we would continue with this, multiply, and then what we do in mathematics, you don't have to write this. I'm trying to help you understand what this would look like in general. We would, whatever n is, we would multiply by subsequently decreasing integers until we got to 1. If we did that in the bottom with n minus 1, we would do the same, n minus 2, and then you'd have an n minus 3, and then we do the same, multiply down till we get 2 times 1. Now look what happens here. The n minus 1's cancel, the n minus 2's. Note, I didn't write an n minus 3 in the numerator, but it's in there within the dots. It's meaning that all of these will cancel, just like we have with the 5 factorial over the 4 factorial. The 4 times the 3 times the 2 times the 1 all cancel. So if you look at all of that will cancel, we are left with n. So we can get rid of all of this and simply say that the left-hand side reduces to n. Over here we have 40, and we have an n minus 4 factorial and n minus 3 factorial. The n minus 3 is the larger of the two. For instance, if n equaled 10, 10 minus 3 is 7, and 10 minus 4 is 6. So all of the when you write out the factorials of those, all of that would cancel except for n minus 3 in the denominator. And now we have an equation where we simply solve. We're going to multiply by n minus 3 on both sides. I'll go ahead and explicitly do that. And that's going to give us, if we kind of look ahead, if we distribute in the n, I'll just go ahead and write it out. N squared minus 3n equals, those cancel there, we're left with 40. And now we have a quadratic, so we have to factor the quadratic by moving the 40 over, setting it equal to 0. Well, the two numbers we're looking for, multiply to be negative 40 and add to be negative 3. Those factored terms would be 8 and 5, positive, negative 8, we had negative 8 and a positive 5. So that would give us n minus 8 times n plus 5. And when we set those equal to 0, n will equal 8, comma, n will equal negative 5. I wrote these separate for a reason. Note we're dealing with positive integers here. So n equals negative 5 is not a possibility. Our final answer is n equals 8. So for number 10, how many ways can 8 different cans of vegetables be placed on a row on a shelf? So when we talk about the difference between counting principles, combinations, and permutations, and note if Mr. Noble or Mr. Sacco's students are watching this, they may not recognize this. I briefly covered this with my students at the beginning of the lesson, so you can just disregard what I'm saying here. But hopefully once we get into the factor or the permutation part of this explanation, it makes sense for those of you who are not my students. So when we look at this and we want to determine which one this is, counting principles, combinations, or permutations, the first question we ask ourselves is, if we make a selection, would we insert it back into the sample space? So if we think of, we have 8 different cans of vegetables, like one are peas, one are corn, one is mixed vegetables, and let's say I want to put them all 8 of them on the shelf. Well, first question we have to ask ourselves, if I choose one of those 8 and put it on the shelf, could I choose that again? Well, obviously not. That can of corn or whatever can of vegetable that we chose is on the shelf. You can't choose it again. That rolls out counting principles. So now we have to determine if it's combinations or permutations. So what we do is we make a selection. And you think about, you to make one selection where, let's say we put the can of corn first, and we do the mixed vegetables for a second, the can of green beans third, and so on. We make a selection, we put it in that order. And then you imagine if we rearranged all of those and ask yourself, is that a different possibility? Well, if I'm in the grocery store and I walk by a shelf, if I have them arranged in different orders, that would matter, because the can of corn coming first on the left is a different arrangement than, for instance, if I had the mixed vegetables first on the shelf. So the order in which they are selected, or the order that they're lined up, matters. Therefore, it makes this a permutation. So we are going to use NPR. That's one way we can do it. I will also show you another way. So if we do NPR, N is the number of cans of vegetables, which is 8. And then R is how many we're selecting. Well, we're putting all of them up on the shelf, so it's 8 pick 8. Now look what happens when you do this. You get 8 factorial, because that's N, over 8 minus 8 factorial, which gives you 0 factorial, which by definition equals 1. So this is equal to 8 factorial. Now, there is a factorial button in your calculator. We'll go over that in class. And if you plug in your calculator or just multiply it out, 8 factorial is equal to 40,320. So there would be 40,320 ways in which we could arrange the cans of corn. Now, what happens if we did it, and what I noted to my students is that permutations, you can also use counting principles to determine a permutation. Again, where the arbitrary nature of, or ambiguity of, permutations, combinations, and counting principles come into play. But nonetheless, it does work. So if you think of, if I have 8 slots for inserting the cans of vegetables, if I think of how many could I insert, well, I have 8 cans, so on my first slot where I'm going to insert my first, or set down my first can of vegetable, I want to know how many possibilities do I have. Well, if I have 8 cans, I could put 8 there, so that'd be 8. Now I put one down, so now I only have 7 possibilities for the second slot, so that would be 7. And since now I put 2 down for the third position or slot, I have 6, and then that would continue all the way down. 3, 2, and for each of these, we have each of the others, meaning we multiply these. And if you look at that, that's 8 multiplied by all the numbers all the way down to 1, which is the exact same thing as 8 factorial. Which indicates to us when we're doing a permutation and you're making selections of all of them, it's just going to be n factorial. So for number 13 here, we want to find the number of possible license plates, each consisting of 3 letters and then 3 digits, given the following parameters. First off, the letters must be different. So given the fact that we have 2 sample spaces, the letters and then numbers, I'm going to do this. I'm going to start out by doing this 1, 2, 3, 4, 5, 6 by saying, okay, we have 6 objects to insert, the first 3, and we're multiplying them. The first 3 are letters, and the last 3 are numbers or digits. And I'm going to talk about it just in the sense of this is really just counting principles by inserting the number of possibilities in each one and multiplying it, and then I'll talk about it in terms of permutations. So first off, for the first three letters right here, the letters must be different. So we know there's 26 letters in the alphabet. So I know in the first case I need 26. Now if I insert A, for instance, there, I can't do A again. So, or if I inserted C, whatever letter I inserted on the first one, I can't insert that again on the next one. So therefore, the next one, we're going to have one less letter, which means we have 25 letters that we can insert there. And now let's say if I insert like C and A into the first and second slot or position, then in the third position we have two less than 26 or 24 possibilities. So it'd be 26 times 25 times 24. There are no restrictions on the numbers, so there are 10 digits, 0 through 9. So we have 10 possibilities here, 10 possibilities here, 10 possibilities here. And that ends up giving us the nice, neat number of 1, 5, 6 with 5 zeros. 1, 2, 3, 4, 5, which is, 15 million, 15.6 million. Okay, now what if I looked at this in terms of counting principles and permutations? Well, in the first part, it says the letters must be different. So I look at these first three cases, and if I insert a letter, I can't insert it again. Therefore, it's not counting principles because we're not inserting back into the sample space. So I have to determine if it's permutation or a combination. So if I make a selection, let's say I make the selection car, C-A-R, and I put them in that order, C-A-R, and then I ask myself, what if I rearrange those letters in a different order, the same letters but in a different order? It doesn't matter what order. Let's say if I change it up to R-A-C, and then I ask myself, is that a different possibility? Well, we know that the word C-A-R is different than the word R-A-C, which means the order of selection matters, which then means it's a permutation. So I would have, excuse me, N would be our 26, N, P, and then our R is the number of selections we're making, which is 3. And we do that calculation by doing 26 factorial over 26 minus 23 factorial. And of course, I'm just trying to explicitly show you how these calculations work out. Oh, whoops, I'm sorry, that's not supposed to be a 23. That's supposed to be just a 3, because it's N minus R. And that would give us 23 in the numerator, or in the denominator, excuse me. So now we see the 23 on down would cancel, and we'd be left with, I'll just write it down here, 26 times 25 times 24, as the 23 on down to 1 all cancel, and if you look, it's exactly the same as what we have up here. Now on the letters, or excuse me, on the digits, we ask ourselves, okay, is it counting principles, permutations, or combinations? So if I have 3 numbers and I'm putting in 3 numbers into 3 slots, I first ask myself, if I insert a number into the first slot, could I insert that again in the next? Well, there are no restrictions, so I could use 0 or 1 or 2, whatever number I make for the first slot, I can make it again for the second, meaning I could have 1, 1, 1, 2, 2, 2, and so on. So that doesn't pass the first test of if we reinsert back into the sample space after making a selection. The answer is yes, we do reinsert, and therefore it's counting principles. And with counting principles, you just do exactly what we do. You draw your lines, insert the numbers, and multiply them.